A warm welcome to all of you. I present this lecture mainly for first semester chemistry students of our college during the critical situation of COVID-19 pandemic. This topic, heat capacity of solids, is present in physical chemistry 1 syllabus of our Bharathasan University. As this lecture is based on syllabus, I want to read the syllabus related with this topic. Unit 4, Statistical Thermodynamics, Heat Capacities of Monatomic Crystals, Einstein Theory and debye Theory, Quantum Statistics, Concept of Negative Kelvin Temperature. This slide shows a request to viewers. Heat capacity of solids. The heat capacity at constant volume and the symbol is Cv, that is change in vibration energy with respect to change in temperature at constant volume. That is Cv is equal to dou E by dou T at constant N and at constant volume V. That is heat capacity of solids. That is a variation of energy with respect to temperature. That is called heat capacity of solids. Next topic, that is Dulong-Petit law on the heat capacities of solids. That is, Dulong and Petit discovered that all investigated solids had a molar heat capacity of approximately 6 calories per Kelvin at around 298 Kelvin or at room temperature. That is, Cv is equal to 3R. That is, for all solid elements, the heat capacity, molar heat capacity value is 3R value at room temperature, that is at around 298 Kelvin. That statement is called as Dulong-Petit law. This slide shows variation of heat capacity with the temperature for some elements. For elements like lead, cadmium, silver and carbon diamond. From this slide, we know that heat capacity value is zero value at absolute zero temperature, and the value increases with the increase of temperature and reaches a value of 3R, that is around 6 calories for most of the elements at room temperature or at around 300 Kelvin. But in this element carbon diamond, that is the exceptional case. For most of the elements, the value is around 6 calories at room temperature or at around 298 Kelvin. That is the variation of heat capacity with the temperature. So any theory used to calculate heat capacities of crystalline solids must explain two things. One is near room temperature, that is at around 298 Kelvin. The molar heat capacity of most solids is around 3R. That is Dulong-Petit law. Another one, at low temperature, Cv decreases and becoming zero at absolute zero temperature. So to explain these two statements, two theories are proposed. One theory was authored by scientist Einstein, another one was authored by scientist debye. But the classical mechanics would predict Cv is equal to 3R at all temperatures in violation of both the experiment and the third law of thermodynamics. I already told two theories. Two main theories were developed to explain the variation of heat capacity with the temperature. The first was given by Einstein, and the theory is known as Einstein theory of heat capacity of solids. And the second one was authored by scientist debye, and that theory, that is called debye's theory of heat capacity of solids. Next topic is Einstein theory on heat capacity of solids. Einstein treated the atoms in a crystal as n-symbol harmonic oscillators, all having the same frequency nu, and the frequency nu depends on the strength of chemical bonds within the solid. Since each atom oscillates in three mutually perpendicular directions, x, y and z directions, n atom solid is equivalent to 3n harmonic oscillators and each vibrating independently at frequency nu. Even though an atom is considered as three-dimensional simple harmonic oscillator, first it is considered as one-dimensional, later a correction is applied for three-dimensional. Now the energy levels of the harmonic oscillators are given by epsilon is equal to n h nu, where n is equal to 0, 1, 2, 3, etc. And this is the equation from quantum mechanics. At thermal equilibrium, the oscillators in a crystal will be distributed among the various allowed energy levels as per Boltzmann distribution law. That is, N0 oscillators in energy level E0 and N1 oscillators in energy level E1 and N2 oscillators in energy level E2 and N3 oscillators in energy level E3 and similarly Ni oscillators in energy level E8. Now the total number of oscillators, that is total number of oscillators, that is N is equal to N0 plus N1 plus N2 plus N3 etc. From Boltzmann distribution law, N1 is equal to N0 e power minus E1 by kT. Similarly, N2 is equal to N0 e power minus E2 by kT. And for ith level, number of atoms, that is Ni is equal to N0 e power minus Ei by kT. So the total number of atoms, oscillators, that is equal to, on applying Boltzmann distribution law, that is equal to N0 plus N0 e power minus E1 by kT plus N0 e power minus E2 by kT plus N0 e power minus E3 by kT plus etc. Now that is the value on applying E is equal to h nu. Now the equation becomes N is equal to N0 plus N0 e power minus 1 h nu by kT plus N0 e power minus 2 h nu by kT plus N0 e power minus 3 h nu by kT plus etc. That can be simply written as N is equal to N0 sigma 0 to infinity e power minus n h nu by kT, and the value of n is from 0 to infinity. Now the total energy E is equal to N0 E0 plus N1 E1 plus N2 E2 plus etc. Now the energy of various levels. For 0th level, energy is 0 and E1, that is equal to 1 h nu, E2, that is equal to 2 h nu, and on applying Boltzmann distribution for number of oscillators in various level, that is N1 is equal to N0 e power minus 1 h nu by kT, N2 is equal to N0 e power minus 2 h nu by kT, and substituting the value of N1, N2, N3 etc. from Boltzmann distribution law, and E1, E2 as a formula from E is equal to n h nu. Now the equation becomes E is equal to N0 into 0 plus N0 e power minus h nu by kT into 1 h nu plus N0 e power minus 2 h nu by kT into 2 h nu plus etc. Now this equation can simply be written as E is equal to N0 sigma 0 to infinity e power minus n h nu by kT into n h nu, and the value of n is from 0 to infinity. The average energy of an oscillator in excess of 0 point energy, that is E bar, that is equal to total energy divided by total number of oscillators, that is E divided by N. Now that is equal to N0 sigma 0 to infinity e power minus n h nu by kT into n h nu divided by N0 sigma 0 to infinity e power minus n h nu by kT. So on simplifying these equations, we get average energy of an oscillator, that is given by E bar is equal to h nu divided by e power h nu by kT minus 1. That is the energy of simple one-dimensional harmonic oscillator according to Einstein. Now the average energy of three-dimensional oscillator in excess of 0 point energy, that is E bar is equal to 3 h nu. That previous equation is multiplied with 3. So E bar is equal to 3 h nu divided by e power h nu by kT minus 1. This is the average energy of three-dimensional oscillator.
Now for 1 mole consists of Avogadro number of atoms. So for 1 mole, E is equal to 3n H nu, 3n H nu divided by e power H nu by kT minus 1. So that is the previous equation is multiplied with Avogadro number, that is capital N. That is total energy of 1 mole of solids according to Einstein. E is equal to 3n H nu divided by e power H nu by kT minus 1. Now on differentiating the energy equation with the temperature, we get the equation for heat capacity of solids. Now the energy equation is E is equal to 3n H nu divided by e power H nu by kT minus 1. And differentiating this equation with the temperature, and the temperature is in the function the denominator. So first differentiation is minus 1 by function square. That is why we get minus 3n H nu divided by e power H nu by kT minus 1 whole square. And differentiating e power H nu by kT minus 1, that is e power H nu by kT first, and then H nu, and differentiating H nu by kT, we get minus H nu by kT square. So on multiplying this equation by k by k and simplifying this equation, we get the final equation, that is 3r, that is because nk is equal to r, n is the Avogadro number, k is the Boltzmann constant. On multiplying these two, we get the value of gas constant, that is r. And therefore the final equation 3r divided by e power H nu by kT minus 1 whole square, e power H nu by kT and H nu by kT whole square. Now on substituting H nu by k as theta e, that is Einstein's characteristic temperature, we get another equation, that is Cv is equal to 3r divided by e power theta e by t minus 1 whole square, and numerator e power theta e by t and theta e by t whole square. Now this equation is called as Einstein's heat capacity equation. Now the Einstein heat capacity equation is shown in this slide, and using this equation one can explain the variation of heat capacity with the temperature. This topic Dulac-Petit law from Einstein equation. That is, we can derive Dulac-Petit law from the Einstein equation. That is, at high temperature, the H nu by kT, the value is very less than 1. So that is, as the temperature is in the denominator, that is the total value of H nu by kT is very low value, and less than 1. So from Einstein equation, E is equal to 3 n H nu by H nu divided by e power H nu by kT minus 1, that is energy for 1 mole, and e power H nu by kT can be written as exponential term, that can be written as 1 plus H nu by kT plus H nu by kT whole square, etc. And as the value of H nu by kT is very small, neglecting third term, from third term, the equation becomes the value of e power H nu by kT is given by 1 plus H nu by kT. So on substituting this value in the energy equation E is equal to 3n H nu divided by, in the place of e power H nu by kT, the value of 1 plus H nu by kT, that is substituted, and the equation is 3n H nu divided by 1 plus H nu by kT minus 1, and on simplifying this equation, first we get 3 nkt, and the value of nk is r, that is 3 RT, E is equal to 3 RT, and differentiating this equation with respect to temperature, we get the value of 3R. This is Dulac-Petit law. Thus the Dulac-Petit law is derived from Einstein equation. Now success of Einstein theory. It explains theoretically that heat capacity increases with the temperature and tends to the value given by Dulac-Petit at high temperature. That is one success. Another success, it also explains that specific heat decreases as temperature falls and tends to be zero at absolute zero temperature. So at high room temperature, the value given by this equation is around 3R, and the value decreases, heat capacity decreases at temperature decreases, and the value of 0 is attained at absolute zero temperature. These are the success of Einstein theory. Next, limitation of this theory. First one, it is an approximate one. Its limitations are more serious at low temperatures. For example, it was observed that in the case of copper, aluminum, etc., the specific heats at low temperature decreased more rapidly than that predicted by Einstein theory. That is one limitation. Another one is Einstein assumed that the vibrations of the atom in a crystal are independent, but the atoms are closely packed in a crystal. The vibrations will be complex. The atoms will behave like dependent particles. These are the two limitations of Einstein theory. Next theory, Debye theory on the heat capacity of solids. In Debye's theory, there are certain assumptions. That is, Debye assumed certain things. What are the assumptions? Because of the close packing of atoms in a crystal, it is evident that they will behave like dependent particles. That is, the atom will not vibrate with the same frequency. The interacting particles will vibrate in a complex manner. The vibrations can be regarded as the series of simple harmonic oscillators with the different frequencies. So in 1 mole of crystal, there are 3n coupled oscillations with 3n different frequencies. The minimum frequency is 0 and the maximum frequency correspond to the wavelength of the order of interatomic distances. Now the problem is to determine frequency distribution. For this purpose, Debye disregarded the atomic structure of solids and treated a solid as a homogeneous, isotropic, elastic medium. The vibrations are considered to be elastic waves propagated in a continuous medium. There are three types of waves. Their displacements are at right angles. The vibration wave, one longitudinal, and the remaining two are transverse. But all the vibrations are in the same direction. But in isotropic crystal, the velocities are independent of directions. These are the assumptions made by Debye, and he derived an equation. That final equation is called as Debye's heat capacity equation. Using that equation, one can explain variation of heat capacity with the temperature. From the theory of elasticity, the number of normal mode of vibration dn for elastic waves moving in a solid of volume V with the frequencies in one direction lying between nu and nu plus d nu, that is given by dn is equal to 4 pi v nu square d nu divided by small v cube, that is velocity. So that is equal to 4 pi v 1 by v L cube plus 2 by V T cube into nu square d nu. Let this equation be 1. Here VL, that is the velocity of longitudinal wave, and Vt, that is the velocity of transverse wave. There are 3n vibration frequencies in a solid containing n atoms. So the integration of the above equation between frequency limits 0 to nu m gives the value of 3n. So the equation becomes 3n is equal to 4 pi v 1 by vl cube plus 2 by vt cube integral 0 to nu m nu square d nu. On integrating and substituting the limits, we get the equation 4 pi v 1 by vl cube plus 2 by vt cube nu m cube divided by 3. From this equation, the value of 1 by vl cube plus 2 by vt cube, that is given by 9n divided by 4 pi v nu m cube. That is by simplifying the equation, the above equation, we get the equation 2. Now on substituting equation 2 in 1, that is the value in the square bracket from equation 2, and the value we substitute in equation 1, we get dn is equal to 4 pi v and 9n divided by 4 pi v nu m cube and nu square d nu. So on simplifying this equation by cancelling 4 pi v numerator and denominator, we get this equation 9n divided by nu m cube and numerator nu square d nu. Let this equation be 3. Now to each degree of freedom, the mean energy assigned as Einstein equation as E is equal to h nu divided by e power h nu by kt minus 1. So the total energy E is equal to integral 0 to nu m h nu divided by e power h nu by kt minus 1 and dn. And the value from equation 3 is substituted for dn. We get this equation E is equal to integral 0 to nu m h nu divided by e power h nu by kt minus 1, and the value of dn is 9n divided by nu m cube, numerator nu square into d nu. So on simplifying this equation, we get 9n divided by nu m cube, that is outside of the integral, and the integral 0 to nu m h nu divided by e power h nu by kt minus 1 nu square d nu. Now on differentiating the energy equation according to d by with respect to temperature, we get heat capacity equation. That equation is called as d by heat capacity equation. Now Cv is equal to dou E by dou T at constant n and constant volume. Now differentiating the above equation energy equation, that is 9n divided by nu m cube integral 0 to nu m, and differentiating 1 by function, that is minus 1 by function square, and h nu that is already the, so minus 1 by e power h nu by kt minus 1 whole square, and differentiating the function, that is e power h nu by kt minus 1, and differentiating this e power h nu by kt, that is e power h nu by kt, and differentiating h nu by kt as minus h nu by kt square, and nu square d nu, that is already there. So on simplifying this equation and multiplying and dividing by k, and simplifying this equation, the final equation, that is 9nk divided by nu m cube integral 0 to nu m e power h nu by kt divided by e power h nu by kt minus 1 whole square, and h nu by kt whole square nu square d nu. So that equation can be written as Cv is equal to 9r, because nk is equal to r. So 9r divided by nu m cube integral 0 to nu m e power h nu by kt divided by e power h nu by kt minus 1 whole square, and h nu by kt whole square nu square d nu. Now this equation is called as d by heat capacity equation, and the d by temperature theta d is equal to h nu m by k, and h is the Planck's constant, and nu m that is a maximum frequency, and max frequency of the oscillator, and k that is Boltzmann constant. Next topic, Dulac-Petit law from d-Buy's theory. According to d by E, energy is equal to 9n divided by nu m cube integral 0 to nu m h nu cube into d nu divided by e power h nu by kt minus 1. Let this equation be 1, and let the value x is equal to h nu by kt, and nu is equal to ktx by h, d nu is equal to kt by h dx, and theta d h nu m by k, and therefore nu m is equal to k theta d divided by h. So on substituting h nu by kt as x, kt nu is equal to ktx by h, d nu is equal to kt dx by h, and nu m as k theta d divided by h. So the equation 1 becomes E is equal to 9n divided by k theta d divided by h whole cube, because nu m is equal to k theta d divided by h, and integral 0 to xm h, and nu is substituted as ktx by h, therefore ktx divided by h whole cube, and d nu is substituted as kt dx by h, and divided by e power h nu by kt is substituted as x, therefore ex minus 1. On cancelling h and k cube, we get the equation E is equal to 9nk t power 4 divided by theta d cube integral 0 to xm x cube divided by e power x minus 1 numerator dx. So that is E is equal to 9r, because nk is equal to r, 9r t power 4 divided by theta d cube integral 0 to xm x cube divided by e power x minus 1 numerator dx. Now this is Debye's integral equation, that is energy equation, integral equation. When t is large, x value, that is h nu by kt, that x value is small. Therefore the equation e power x, that can be written as 1 plus x by cancelling other terms, x square plus x cube, by cancelling other terms, e power x is equal to 1 plus x. Therefore e power x minus 1, that is equal to x. So now the energy equation, E is equal to 9 RT power 4 divided by theta d cube integral 0 to xm x cube divided by x, because e power x minus 1 is substituted x, and dx, that is equal to 9 RT power 4 divided by theta d cube integral 0 to xm and x cube divided by x, that is x square dx. And on applying the limits, upper limit and lower limit, and upper limit is xm. And now the equation becomes 9 RT power 4 divided by theta d cube, applying upper limit xm cube divided by 3 and lower limit is 0. So the equation 9 RT power 4 divided by theta d cube, theta d cube divided by 3 t cube, because xm is equal to theta d divided by t, theta d divided by t. So on simplifying these equations by cancelling theta d and the simplifying the number 9 divided by 3 as 3, so temperature t power 4 is cancelled with t power 3, so the remaining term is t. So the balance equation is 3RT, E is equal to 3RT. Now on differentiating this equation we get the value 3R. This is Dulong-Petit law. Thus Debye's theory is reduced to Dulong-Petit law at a high temperature. Now at low temperature, Debye's third power law is obtained. So the energy equation 9 RT power 4 divided by theta d cube integral 0 to xm x cube divided by e power x minus 1 dx, that is the energy equation, energy integral equation. Now at low temperature, the value of the integral is evaluated as pi power 4 divided by 15. So on substituting the value of the integral in the above equation, E is equal to 9 RT power 4 divided by theta d cube pi power 4 divided by 15. So on differentiating this equation, Cv is equal to, on differentiating this equation with the temperature at constant volume, so equation Cv is equal to 9R, and differentiating t power 4, that is 4t power 3, and the remaining terms 5 power 4 divided 15 divided by theta d cube. So on simplifying the equation by substituting the value of R and multiplying with the 9 and 4 and the value of pi power 4 divided by the number 15, we get another value. The value is 464.4, and therefore Cv is equal to 464.4 t divided by theta d cube. Now this is Debye's third power law. For a given substance, Debye's characteristic temperature theta t is a constant. Therefore Cv is equal to A into t cube, where A is the constant. A is the constant, and the equation Cv is equal to 464.4 t divided by theta d whole cube. That equation is called as Debye's third power law. So at a low temperature, this equation is obtained, that is called Debye's third power law. Next one is weakness of Debye's theory. One weakness, it is assumed that when a solid is heated, elastic vibrations exist within the body having frequencies 0 to neon. The solid is treated as isotropic elastic body. The vibrations are elastic waves in a continuous medium. Even if a solid is an isotropic elastic body, it cannot be treated as continuous, because a solid is composed of atoms separated in space. That is one weakness. Another one is Debye has omitted crystal structure of solids, and third one is near absolute zero, the theory is not accurate. These are the weakness of Debye's theory. Next topic is concept of negative Kelvin temperature. According to Maxwell-Boltzmann distribution law, N2 divided by N1 is equal to e power minus within the bracket E2 minus E1 divided by KT Now here N2 and N1 are the population of upper and lower level, and E2 and E1 are the energy of upper and lower level, and K is the Boltzmann constant, T is the temperature. So I am taking logarithm, and by simplifying for T is equal to minus within the bracket E2 minus E1 and divided by K Boltzmann constant within the bracket ln N2 minus ln N1. And here, if a system has an infinitive energy levels, an increase of temperature favors increased population of higher and higher energy level, but no energy level ever gets populated more than lower level. That is, upper level is never populated more than lower level, never populated than lower level. Okay, so the ratio n2 by n1 is always less than 1 because n1 is greater than n1 is greater than n2. So the as per equation, this t is equal to numerator negative sign, and the denominator as n1 value is greater than n2, the denominator value is also negative. So the T value negative divided by negative, that is positive. The temperature is positive. Now at infinitive temperature, as T is equal to infinitive, N would be equal to N2. N would be equal to N2. But this would require an infinite amount of energy because of the infinitive number of energy levels. So for the sake of argument, that a system capable of existing in only two energy levels, E1 and E2, E2 is always greater than E1. At positive temperature, the lower level is more populated than upper one, that is N1 is greater than N2. If the two levels are equally populated, that is N1 is equal to N2, that is in other words N2 by N1 is equal to 1, then as per equation T is equal to minus E2 minus E1 and divided by K Boltzmann constant K ln N2 minus ln N1. The temperature is infinitive because the denominator value is equal to 0. The denominator value is 0, so anything by 0, that is infinitive. So if the two levels are equally populated, then the temperature is infinitive. Now if the upper level is more populated than lower level, that is N2 is greater than N1, then as per equation T is equal to minus E2 minus E1 divided by K ln N2 minus ln N1. The value temperature is negative because the denominator is positive. Now this temperature is called as negative Kelvin temperature. Negative Kelvin temperature means that is beyond the infinitive temperature. So if upper level is more populated and the system is in the state negative Kelvin temperature. These are about negative Kelvin temperature. Now this slide shows a problem related with the determination of nu m value. So the problem is calculate the maximum vibrational frequency of gold atom in the solid state given that characteristic temperature of gold is 170 degree Kelvin. That is theta d is given, and data asked is nu m. So theta d, we know theta d is equal to h nu m by k. H is the Planck's constant, k is the Boltzmann constant, and nu m is the maximum vibrational frequency. So nu m is equal to k theta d divided by h, and substituting the value of Boltzmann constant and d by characteristic temperature and Planck's constant, we can simply calculate the value of nu m. With this, I want to conclude my lecture on heat capacity of solids. This topic is very important in the examination point of view. Questions asked frequently in these topics, that is, explain Einstein theory of heat capacity of solids and explain Debye's theory of heat capacity of solids, and one more question, that is explain negative Kelvin temperature. These questions are frequently asked in the university examination. I express my sincere thanks to all viewers, and also I want to get positive and negative comments from viewers.
that makes me the future lecture in a better way. Once again, I thank one and all. Thank you.